66A, we're going to begin taking a look at inverse functions. And I want to start this lesson by asking you to take a quick look at these two functions, f and g, and see if you can figure out what makes them an interesting pair. There is something very interesting about these. What is it? Pause. Come back. Okay. Well, did you notice that what they do at the inputs is like exactly the opposite? In other words, what does f do with its input? It takes its input, it squares it, and then it adds 2. What does g do with its input? Does it do the same thing, square it and add 2, subtract 2 square root? Notice that's exactly the opposite, in the opposite direction and everything. And of course you could say the same thing. You say what g does, f does the opposite. What am I going to do at the input? I'm going to subtract 2 and then square root. Well, yeah, I'm going to square it and add 2. So it's like one takes back what the other one just did. So I'm going to write that out here. What f does, or let's write it this way. F and g do exactly the opposite things with their inputs. Exactly the opposite things with their inputs. And this is what we mean by being inverse functions. They're inverses because one, like I say, takes back what the other one did. They're like they undo each other in some sense. To show this undoing effect, I like to usually draw like an assembly line. Think of f of x as a machine. Think of g of x as a machine. It's a machine because you feed something into it and it goes stomp, 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 and then it spits something back out, right? So you think of this f of x as a machine. This is a conveyor belt. Think of a conveyor belt. We got these two machines on a conveyor belt. We're going to process some input. So the natural flow is to go like this, okay? So let's say you take some input. I don't know. Let's do like a, let's change colors. Let's do like a 5. So this 5, you have to picture it coming along on the conveyor belt, and then it goes into the f of x machine, and then the f of x goes chomp, chomp, chomp. It takes the 5, it squares it, and then it adds 2. So that comes out as a 27. Cool. So we got the 27 coming out. And then what happens? Well, this 27 gets fed into the g machine over here. And what's the g do? It takes the 27. First it subtracts 2, which is 25. And then it takes the square root and 5. So notice the 5 went in, the 5 came out. Chickens go in, chickens come out. I think that's a line from a movie. Anyway, and it works both ways. In other words, I could have drawn this. I could have put the g of x function first. And it is actually important that it does work both ways. If it doesn't work both ways, you wouldn't actually say that they were inverses. It does have to, in fact, work both ways. But, let's take I don't know, want to put the same thing in? You want to put a 5 in? Let's put a 5 in again. So you put the 5 in, it rolls into the g of x function, and over here the 5 gets processed, so to speak. So the g says, oh, 5. I'm going to subtract 2, it's 3, I'm going to take the square root. So you're getting out basically radical 3. And then the radical 3 goes rolling into the f of x machine, and it gets chomped on. So you take the square root of 3 and you square it, it's a 3 again. You add 2, it's a 5 again. So again, what goes in comes out. That's what I mean when I say one function does exactly the opposite of the other. It means you can kind of hitch them up in a chain, and in the end, nothing happens. In the end, it's like nothing happened. I put the 5 in, well, I got the 5 out again. I put the 5 in, I got the 5 out again. Right? If that's assuming it goes through both machines in either order. Like I say, either order. It's not supposed to matter what order you go in. Okay, in fact, this has an official name, so I might as well put that there right now. This is actually called the fundamental property of inverses. And it's fundamental, so we should write it down. The fundamental property of inverses. We're talking about inverse functions, of course. Fundamental property of inverses, and it goes something like this. If f of x and g of x are a pair of inverse functions, in other words, one's the inverse of the other. If f of x is a pair of inverse functions, then, how should I say this? plugging any value for x into f and the result into g gives back the same value of x. I guess I don't quite have room to do it that way. This gives back the same value of x. And it has to work both ways. Plugging in the same value of x into g and then the result into f gives you back the same value. It has to work both ways. It has to work both ways. It has to work both ways. Now I need to make a very important side note. So now I need a new color. Side note, but it's important. So important side note. Important side note. And it seems to be kind of worth covering here. This important side note is there's an old Yiddish proverb. For example is not proof. I forget where I saw that, but assuming the source was correct, it really is a Yiddish proverb. So the Yiddish proverb, for example, is not proof. So it's important to keep in mind that for these two functions here that we were just playing with, I was saying, look, you put a 5 in, you get a 5 out. And if you do the two functions in opposite ways, instead of f and then g, you do g and then f, you put the 5 in, you get the 5 out. Have I proved that they're inverses? That does not count as proof. That counts as an example. That counts as demonstrating plausibility, I guess. It's like, yeah, they could be. Look, it worked for 5. It worked. So yeah, they really could be. It's a better argument, of course, to be talking about, well, look, I mean, it does exactly the opposite with the inputs. That wouldn't be a bad argument. But in general, because not all functions are going to be that obvious, they'll be inverses, but you won't be able to tell just by looking at them. So it's important to know that in general, for example, is not proof. Therefore, let's write this out some more. Maybe I'll stay in red because it's still important here. So you can use this fundamental property of inverses, the idea that you plug one into the f and then result into the g and you get back your original whatever. You can use the fundamental properties to prove f and g are inverses you can do it, but you must work in terms of what I'll call a free, these thick pens are bumming me out here, a free, in other words, unspecified x. You don't make up a number for x. You just say, well, for all x's that I would ever care to make up, it'll work. I.e. do this. What are you trying to tell me to do here? I'm trying to tell you to do this. Show that when you plug x into f and the result goes into g, you get back x, and when x goes into g and then the result goes into f, you get back x. By the way, haven't we seen this kind of a thing before? Let's look at this in the opposite direction. This is kind of like saying if you plug x into f, right? So that's, let me make some more room for myself. If I plug x into f, that's what this means, right? If I plug the result into g, well, that's what this means, right? I'll get back my x. Remember what that's called? That's called a composition of functions. That should remind you of the last lesson. Say, oh yeah, we did that. And then this is saying plug x into g, which means do this, find g of x. Then take the result and plug it into the function, okay, and then you'll get back your x. Both. You have to show both. Show both. If you can show that plugging the f function into the g function gives you just x, and if you can show that plugging the g function into the f function gives you just x, then you have demonstrated that they are inverse functions. So for an example, let's take our two functions that we were just playing with. Now we convinced ourselves, or I did anyway, that just from considering what happens to the inputs, it's like, well, it's doing exactly the opposite thing to the inputs. They have to be inverses. So we kind of suspect this is going to work, but let's do a formal proof. So prove that f of x equals x squared plus 2 and g of x equals the square root of x minus 2. Let's prove that those are inverses. Well, you have to go like this. You have to plug f into g. Plug g of x into f of x. And what have I got here? Well, that would mean taking this g function and using it as the input for the f function. So where I see the x, I'm putting the entire square root of x minus 2 thing. Now that input is supposed to get squared, and then you add 2. Notice how nicely this is going to simplify, because the square is going to basically take off the square root, and you're going to have an x minus 2, and then plus this plus 2 here. And that really is just an x. That was nice. I mean, it looks like a lot of work. Oh my gosh, I got to plug functions into each other. But the good news is it's supposed to simplify quite nicely. It's supposed to just simplify to an x. And it did. But you have to show it both ways. Don't forget to show it both ways. Now we have to plug the f function into the g function. So here's the f function. Use that as the input over here. Plug it in there. So I would have, let's see, I'd have a square root of, okay, time for the input. The input's going to be the entire f function. Okay, and then don't forget that minus 2. Now, of course, the parentheses don't really matter here, right? Because it's like a positive 1 in front. I can kind of ignore those parentheses and just say, well, the plus 2 and the minus 2 are going to cancel. So it's the square root of x squared, which is indeed an x. I need to make a careful point here in a second, but that's how you prove that they're inverses, both f of g and g of f. You plug one function into the other, you plug the other function into the one, and both times they reduce to just x. That counts as a proof. Some people, if I ask them to prove that they're inverses, they might say, well, it worked for 5, it worked for 6, it worked for -3. Yep, it works. That's proof. That's not proof. For example, it's not proof. You have to do it this way. You have to do it working in terms of an unspecified general sort of a free value of x. Okay, I got to just throw a little side note in here. This will actually come up later, so it's important to note this. That, is this really true? Is the square root of x squared really x? Could be, but only if x happens to be not negative. If x was negative, this wouldn't work. Watch. Let's say x is -3, right? Well, if I take a -3 and I square it, that looks like this. And if I take radical 9, I get a 3. Okay, I was supposed to write x equals -3. So if x is -3 and I square it, I get a 9. Well, radical 9 is just 3. So that doesn't work. This is not x. X is not 3. X is -3. So it doesn't work when x is negative. And it goes back to the idea that this symbol by itself, this radical symbol, only indicates the positive root. When you're solving equations and you take the square root of both sides, we always put a plus or minus in front, and that's because every number really does have 2 square roots. So if you're solving an equation and you want the square roots, you want both, you have to write the plus or minus. But if the plus or minus is not written there, then you assume it means the positive root. And this function, there was no plus or minus in front. In fact, if there was, it wouldn't be a function, right? It would fail the vertical line test. There was no plus or minus in front, so you can't put one in here. So anyway, what I'm saying is, yes, this works, but we have a domain restriction. X has to be greater than or equal to 0. Luckily, they did say that in the first place. So happy. Life is happy. Okay, cool. So I've given you sort of a, that was kind of a trivial example, I suppose. Those two functions weren't too hard to deal with, and we kind of knew already that they were inverse functions. But get a load of these two functions right here. Look at those two. Would you say that, oh yeah, what that does with the input is exactly the opposite of what that does with the input? Because after all, what this does with the input is it adds 3, stores the value, and divides by twice the input. And what this does is it doubles the input, subtracts 1, and that doesn't, you can't tell by looking at that, right? You don't know. But they are inverses, and I can prove it to you. How do I prove it? I use the fundamental property of inverses. I have to show both. So I'll say using fundamental property of inverses. We need to show, one, that if you plug the g function into the f function, it's just x. And you need to show the other thing too, that if you plug the f function into the g function, it simplifies to just x. Again, the good news, it is supposed to simplify to just x, so the math can't get too intense anyway. So anyway, let's do the first part. We're going to plug the g into the f. So I'm using the entire g function as the input, plugging it in here, plugging it in there. What's that look like? That's going to look like, okay, take the input, which is 3 over 2x minus 1. Okay, add 3. That's on top. On the bottom, 2 times, put the input in, 3 over 2x minus 1. Okay, so yeah, it doesn't look too pretty at the moment. So let's play with the top here. What we have is basically we want to be able to add 2 fractions together. So the first thing you would do is make the 3 look like a fraction. And then the next thing you would do is you'd say, well, I need a common denominator of 2x minus 1. So let's do that. Okay, so that's setting up the top. And the bottom here, remember that 2 is like a 2 over 1, and it's going to have to multiply this. So that's kind of setting up the bottom. Now let's play with some fractions here. So notice that we have a common denominator here. So we can just add across the tops, right? Add across the tops. So I've got 3 plus 3 times 2x minus 1 all over the 2x minus 1. And then down here, well, I got 2 times 3 is 6 on top all over the 2x minus 1. Now at this point, feel free to just cancel those. I'm dividing by 2x minus 1. I'm dividing by 2x minus 1. Okay, they're doing the same thing. You can cancel that then, especially if you can get the eraser to work. Okay, so where are we? We are here now. So coming across the top, I got a 3 plus, and if I do that distributing, I'll have a 6x minus 3. And then these are canceled now, so that's all over a 6. So notice the 3 minus 3 cancels. I've got a 6 over 6. The 6's cancels. It really is just x. Yay! I always love that part. It gets simpler, and you know, that starts intense looking, but it's supposed to simplify quite nicely, and it did. If it didn't, you would conclude right away, these are not inverses. But anyway, let's do the opposite now. So now we got to do g of f, which means we have to take, well, that was f of g. Now we have to do g of f. And g of f is going to be g of f. Means the f goes into the g as the input. It doesn't go there. It doesn't go there. It goes there. So you take the whole f function, plug it into the g function. What are we going to get here? We're going to have a 3 on top. Let's kind of divide this. We have 3 on top over 2 times the input. The input is the entire f function minus 1. All right. So the top is just a 3. That's good news. The bottom. Again, think of that as a 2 over 1. So it's like having a 2 times an x plus 3 on top and a 1 times a 2x on the bottom. And you know what? Well, minus 1. I feel like canceling those 2's, don't you? So I've got 3 over, I've got an x plus 3 over an x right here, minus. Now that's a 1, which is like 1 over 1. And then I need to make it into an x over x. Looks hideous. I'll just call it an x over x. Anything over itself is 1, right? So there, that's a 1. Okay, nobody likes hideous. So anyway, 3 on top. What do we got on the bottom now? Well, now I can subtract across the tops, right? And if I subtract across the tops, I have x plus 3 minus x. I guess I'll write it out. And that's over the x, right? You carry the denominator along when you add your fractions. Okay, so what I got? I got a 3 on top. On the bottom, the x plus 3 minus the x is basically a 3 over x. Remember how to unstack your fractions. This means the top is being divided by the bottom, and the way you do that, the way you divide fractions is you multiply by the reciprocal, and then lo and behold, the 3 cancels, you really do just get x. Ain't that something? It worked. It so worked. So those really are inverse functions. They are a pair of inverses. Who'd have thunk it, right? Okay, so now that we kind of know what a function is, and we know how to prove whether, or what an inverse function is, and we kind of know how to prove whether two functions are inverse pairs or not, turns out if you graph them up, they have some really interesting properties. So this is back to our original pair, the first two functions we looked at. So let's just graph them up and go, So with this one, and oh, by the way, I was supposed to write that the domain here, we're supposed to be restricting ourselves to this, and the domain here, we're supposed to be restricting ourselves for this. In the next lecture, I'm going to explain why that's actually important for this problem. But for now, just, we're going to do that. We're going to restrict ourselves. So let's graph these things. We could make XY tables. Well, I suppose I could. Just going to go like this. If you plug... Now we're only allowed to plug in things that are greater than or equal to 0, so let's not plug in any negatives here. So if I plug in a 0, 0 squared plus 2 is a 2. If I plug in a 1, 1 squared plus 2 is a 3. If I plug in a 2, 2 squared plus 2 is a 6. Okay, that's good enough. So I've got the point 0, 2, which maybe I'll list that right here. I've got the point 1, 3, which I'll list it out here for reference. And I got the point 2, 6. Okay, cool. Just put the points out here for reference, and it's basically it's a parabola, right? X squared, it's some kind of parabola. It's the right half of a parabola anyway, so I'm just going to kind of go like this and say there's our f function. Cool. Now let's graph this one. So I'll make a new xy table, or xg of x table, and we're allowed to plug in things greater than or equal to 2, so let's start at 2. If I plug a 2 in there, 2 minus 2 is 0, and the square root of 0 is, guess what, 0. And actually, let's be a little strategic. Oh, plugging in a 3 looks good, actually. 3 minus 2 is 1. Square root of 1 is 1. Fine. Do I want to plug in a 4 in? No, because I don't want to be thinking about square root of 2. Plug a 6 in. That'll do. Because a 6 minus 2 is a 4, and I can take square root of 4 and get 2. See, now we're talking. Be a little strategic when you're plugging in. Anyway, I got some nice points here. Let's do it up. X is 2, y is 0, boink. X is 3, y is 1, boink. X is 6, y is 2, boink. So here's our g function, something like this. It's a square root function. And for reference, that was the 0.20, that was the 0.31, that was the 0.6, 2. Okay, cool. So looking at, and that's a g. Looking at these two graphs here, what do you notice? There are... Does it say it at the top? It does. There are 4 big properties of inverses, and you should be able to just look at this and see 3 of them anyway, if you look hard enough. What's the first thing you notice? Let's get a new color. First thing I notice is I notice this right away, actually. Look at this point, 0, 2, 2, 0. 1, 3, 3, 1. 2, 6, 6, 2. It's like the x's and the y's are just kind of changing roles or something. Maybe I'll say, maybe I'll say with a pen, it's like the x's and y's are switched. Now, if I want to say that more formally, you'd say it like this. For every point, and let's just, A comma B or something. For every point on one graph, you will find the point B comma A on the other graph. I got 3 comma 1. I got 1 comma 3. So whatever you make up, AB becomes BA. It's like XY becomes YX. So that's actually cool. That's big. Here's another point. Looks like I need to write smaller. Well, I'll do that later. What else? Well, this is kind of a corollary of that. If you think about domain and range, maybe I'll just state it and then show you. So the domain of one is the range of the other, and it works both ways. In other words, F's domain is, remember, it's the set of all acceptable inputs. And actually we wrote up here that we were only going to accept numbers that were greater than 0. So if you use the interval notation, you'd say start at 0, include 0, square bracket, start at 0, go all the way up to infinity. You cannot include infinity. Infinity is not a number. It's a notion. Keep going. It's just a notion. It's not a number. So anyway, so you go from 0 to infinity, and look at the range, I guess, of f. That would be the set of all the y values, the outputs, the set of all possible outputs. And since we had to start at x equals 0, notice the y value never goes below 2. So the y value starts at 2, and then it climbs up to positive infinity. Okay, cool. Now, look at the domain of g. The domain is, well, it starts at x equals 2 and it keeps going. See what I mean? It's the same as the range. And now look at the range of g. Here you're looking at the y values. What's the set of all possible outputs? And you'll notice that because g starts here, you never get y below 0. There's no negative y's here. So the range is y starts at 0 and climbs all the way. This is a square root. It climbs more and more slowly, but it does keep climbing. So 0 to infinity. The same as the domain. So that's what I was saying. The domain of this is the same as the range of this. The range of this is the same as the domain of this. They switch. And I call it a corollary because, well, they must, because what we just said earlier, a second ago here, is we just said that the x's and y's switched, right? So a 1, 3 becomes a 3, 1. Well, if you switch all the x's and all the y's, then the domain becomes the range, and the range becomes the domain. So, okay, cool. So that's 2 good properties down. What's another property? Well, if you think in terms of like mirrors and reflections and things, notice how if you kind of folded the paper along the diagonal, and by the way, the equation of this line would be slope of 1, y-intercept of 0, y equals x. So if you folded the paper along that diagonal, notice it's a reflection. This point sort of reflects to this point sort of reflects to this point, and so on. So they are reflections about the diagonal line. So I'm going to call that our third property, 3. Their graphs are reflections over the diagonal line, which is given by the equation y equals x. 3 really good properties right there. We're almost there, folks. I said there were 4. I need to shrink this up so we have a little more space. There we go. Fine. Okay, and then the other property is actually the one that we stated on the previous page. So you're not necessarily seeing it on the graph, but the old fundamental property of inverses. It's fundamental. You have to list that one. So the fundamental property of inverses, which you can state a couple different ways. One way we stated it was we said f of g of x is the same as g of f of x, because either way you do it, it's supposed to simplify to just x. That's a great way to say it. A little more condensed than we said it before. Or you want to say it even more condensed? Remember, this is called a composition, right? You plug one function into the other. And we had a nice special symbol for composition. Oops, let's make sure that looks like an open circle. F open circle G is the same as G open circle F. They both reduce to just X. So you can say it either way, of course. But it's nice to take advantage of these notations sometimes. So speaking of notation, just add a little thing here. If you have an inverse function, the inverse of a function f of x, we don't usually call it g. We usually give it a special name. It's usually denoted like this. F with like a little -1 there. Now I have to point something out so you don't fall for this. Don't make this mistake. This is not an exponent. It's a notation. It's a notation. Just like this doesn't mean multiply f times x. It's a notation, right? It's a notation that means f of x. Similar deal. That -1 is a notation, not an exponent. So there, some people, raise things to the -1 power, and it's like that's got no place, no place in what we're talking about today. So, just to restate the fundamental property of inverses one more time. One more time. You could say that if you plug the inverse into the function, or you plug the function into the inverse, you get just x. You could also say I really want to make sure that looks like an open circle. F composed with f inverse is the same as when you compose f inverse with f. In either case, the result ultimately just reduces to x. Okay, so this idea that this and this both equal to x. Notice it's a nice way of saying it has to work both ways. Make sure when you check it both ways. Okay, we can stop there for today. Next time we're going to look at how do you actually find an inverse, which is cool.